An exoplanet or extrasolar planet is a planet that does not orbit Earth's Sun and instead orbits a different star, stellar remnant, or brown dwarf. Over 1,800 exoplanets have been discovered. There are also free-floating planets, not orbiting any star, which tend to be considered separately, especially if they are free-floating gas giants, in which case they are often counted, like WISE 0855 or Euro 0714, as low-mass brown dwarfs. The Kepler mission space telescope has also detected a few thousand candidate planets, of which about 11% may be false positives. There is at least one planet on average per star. Around 1 in 5 Sun-like stars have an Earth-sized planet in the habitable zone, with the nearest expected to be within 12 light-years distance from Earth. Assuming 200 billion stars in the Milky Way, that would be 11 billion potentially habitable Earths, rising to 40 billion if red dwarf stars are included. The free-floating planets in the Milky Way possibly number in the trillions. On February 26, 2014, NASA announced the discovery of 715 newly verified exoplanets around 305 stars by the Kepler Space Telescope. These exoplanets were checked using a statistical technique called verification by multiplicity. Prior to these results, most confirmed planets were gas giants comparable in size to Jupiter or larger as they are more easily detected, but the Kepler planets are mostly between the size of Neptune and the size of Earth. The nearest known exoplanet, if confirmed, would be Alpha Centauri b, but there is some doubt about its existence. Almost all of the planets detected so far are within the Milky Way. However, there have been a small number of possible detections of extragalactic planets. As of March 2014, the least massive planet known is PSRB 1257 plus 12a, which is about twice the mass of the Moon. The most massive planet listed on the NASA Exoplanet Archive is Dennis PJ 82303.1-491201b, about 29 times the mass of Jupiter, although according to most definitions of a planet, it is too massive to be a planet and may be a brown dwarf instead. There are planets that are so near to their star that they take only a few hours to orbit, and there are others so far away that they take thousands of years to orbit. Some are so far out that it is difficult to tell if they are gravitationally bound to the star. For centuries philosophers and scientists supposed that extrasolar planets existed, but there was no way of detecting them or of knowing their frequency or how similar they might be to the planets of the solar system. Various detection claims made in the 19th century were rejected by astronomers. The first confirmed detection came in 1992, with the discovery of several terrestrial mass planets orbiting the pulsar PSRB 1257 plus 12. The first confirmation of an exoplanet orbiting a main sequence star was made in 1995, when a giant planet was found in a 4-day orbit around the nearby star 51 Pegasi. Some exoplanets have been imaged directly by telescopes, but the vast majority have been detected through indirect methods such as the transit method and the radial velocity method. The discovery of extrasolar planets has intensified interest in the search for extraterrestrial life, particularly for those that orbit in the host star's habitable zone where it is possible for liquid water to exist on the surface. The search for extrasolar planets prompts the study of planetary habitability, which considers a wide range of factors in determining the suitability of an extrasolar planet for hosting life. Definition: IAU, the official definition of planet used by the International Astronomical Union, only covers the Solar System and thus does not apply to exoplanets. As of April 2011, the only definitional statement issued by the IAU that pertains to exoplanets is a working definition issued in 2001 and modified in 2003. That definition contains the following criteria. Objects with true masses below the limiting mass for thermonuclear fusion of deuterium that orbit stars or stellar remnants are planets. The minimum mass size required for an extrasolar object to be considered a planet should be the same as that used in our solar system. Substellar objects with true masses above the limiting mass for thermonuclear fusion of deuterium are brown dwarfs, no matter how they formed or where they are located. Free-floating objects in young star clusters with masses below the limiting mass for thermonuclear fusion of deuterium are not planets, but are sub-brown dwarfs. alternatives. However, the IAU's working definition is not universally accepted. One alternate suggestion is that planets should be distinguished from brown dwarfs on the basis of formation. It is widely believed that giant planets form through core accretion, and that process may sometimes produce planets with masses above the deuterium fusion threshold. Massive planets of that sort may have already been observed. Brown dwarfs form like stars from the direct collapse of clouds of gas, and this formation mechanism also produces objects that are below the 13 mJUP limit and can be as low as 1 mJUP. Objects in this mass range that orbit their stars with wide separations of hundreds or thousands of AU and have large star-object mass ratios likely formed as brown dwarfs. Their atmospheres would likely have a composition more similar to their host star than accretion-formed planets, which would contain increased abundances of heavier elements. Most directly imaged planets as of April 2014 are massive and have wide orbits, so probably represent the low mass end of brown dwarf formation. Also, the 13 Jupiter mass cutoff does not have precise physical significance. Deuterium fusion can occur in some objects with mass below that cutoff. The amount of deuterium fused depends to some extent on the composition of the object. The Extrasolar Planets Encyclopedia includes objects up to 25 Jupiter masses, saying, "The fact that there is no special feature around 13 mJUP in the observed mass spectrum reinforces the choice to forget this mass limit." The Exoplanet Data Explorer includes objects up to 24 Jupiter masses with the advisory, "The 13 Jupiter mass distinction by the IAU Working Group is physically unmotivated for planets with rocky cores, and observationally problematic due to the SINI ambiguity." The NASA Exoplanet Archive includes objects with a mass equal to or less than 30 Jupiter masses. Another criterion for separating planets into brown dwarfs, rather than deuterium burning, formation process or location, is whether the core pressure is dominated by Coulomb pressure or electron degeneracy pressure. History of detection, early speculations. In the 16th century, the Italian philosopher Giordano Bruno, an early supporter of the Copernican theory that the Earth and other planets orbit the Sun, put forward the view that the fixed stars are similar to the Sun and are likewise accompanied by planets. In the 18th century, the same possibility was mentioned by Isaac Newton in the General Scholium that concludes his Principia. Making a comparison to the Sun's planets, he wrote, "And if the fixed stars are the centers of similar systems, they will all be constructed according to a similar design and subject to the dominion of one." Discredited claims. Claims of exoplanet detections have been made since the 19th century. Some of the earliest involve the binary star 70 Ophiuchi. In 1855, Captain W. S. Jacob at the East India Company's Madras Observatory reported that orbital anomalies made it highly probable that there was a planetary body in this system. In the 1890s, Thomas J. J.C. of the University of Chicago and the United States Naval Observatory stated that the orbital anomalies proved the existence of a dark body in the 70 Ophiuchi system with a 36-year period around one of the stars. However, Forrest Ray Moulton published a paper proving that a three-body system with those orbital parameters would be highly unstable. During the 1950s and 1960s, Peter van der Kamp of Swarthmore College made another prominent series of detection claims, this time for planets orbiting Barnard's star. Astronomers now generally regard all the early reports of detection as erroneous. In 1991, Andrew Lyne, M. Bales and S. L. Schemmer claimed to have discovered a pulsar planet in orbit around PSR 1829-10, using pulsar timing variations. The claim briefly received intense attention, but Lyne and his team soon retracted it. Confirmed discoveries. The first published discovery to receive subsequent confirmation was made in 1988 by the Canadian astronomers Bruce Campbell, G. A. H. Walker, and Stevenson Yang of University of Victoria and University of British Columbia. Although they were cautious about claiming a planetary detection, their radial velocity observations suggested that a planet orbits the star Gamma Cepheus. Partly because the observations were at the very limits of instrumental capabilities at the time, astronomers remained skeptical for several years about this and other similar observations. It was thought some of the apparent planets might instead have been brown dwarfs, objects intermediate in mass between planets and stars. In 1990 additional observations were published that supported the existence of the planet orbiting Gamma Cephei, but subsequent work in 1992 again raised serious doubts. Finally, in 2003, improved techniques allowed the planet's existence to be confirmed. On January 9, 1992, radio astronomers Alexander Wolszczyn and Dale Frail announced the discovery of two planets orbiting the pulsar PSA 1257+12. This discovery was confirmed, and is generally considered to be the first definitive detection of exoplanets. Follow-up observations solidified these results, and confirmation of a third planet in 1994 revived the topic in the popular press. These pulsar planets are believed to have formed from the unusual remnants of the supernova that produced the pulsar, in a second round of planet formation, or else to be the remaining rocky cores of gas giants that somehow survived the supernova and then decayed into their current orbits. On October 6, 1995, Michel Mayor and Didier Queloz of the University of Geneva announced the first definitive detection of an exoplanet orbiting a main sequence star, namely the nearby G-type star 51 Pegorsi. This discovery, made at the Observatoire de Haute-Provence, ushered in the modern era of exoplanetary discovery. Technological advances, most notably in high-resolution spectroscopy, led to the rapid detection of many new exoplanets. Astronomers could detect exoplanets indirectly by measuring their gravitational influence on the motion of their parent stars. More extrasolar planets were later detected by observing the variation in a star's apparent luminosity as an orbiting planet passed in front of it. Initially, most known exoplanets were massive planets that orbited very close to their parent stars. Astronomers were surprised by these hot Jupiters, because theories of planetary formation had indicated that giant planets should only form at large distances from stars. But eventually more planets of other sorts were found, and it is now clear that hot Jupiters are a minority of exoplanets. In 1999, Upsilon Andromedae became the first main sequence star known to have multiple planets. Other multiple planetary systems were found subsequently. As of August 14, 2014, a total of 1815 confirmed exoplanets are listed in the Extrasolar Planets Encyclopedia, including a few that were confirmations of controversial claims from the late 1980s. That count includes 1130 planetary systems, of which 466 are multiple planetary systems. Kepler 16 contains the first discovered planet that orbits around a binary main sequence star system. Candidate discoveries. October 17, 2012 brought news of an unverified planet, Alpha Centauri bb, orbiting Alpha Centauri b, which is one of three stars in a triple-star system nearest to Earth's Sun. Alpha Centauri bb is an Earth-sized planet, but not in the habitable zone within which liquid water can exist. As of March 2014, NASA's Kepler mission had identified more than 2,900 planetary candidates, several of them being nearly Earth-sized and located in the habitable zone, some around Sun-like stars. Detection methods. Direct imaging. Planets are extremely faint compared to their parent stars. At visible wavelengths, they usually have less than a millionth of their parent star's brightness. It is difficult to detect such a faint light source, and furthermore the parent star causes a glare that tends to wash it out. It is necessary to block the light from the parent star in order to reduce the glare, while leaving the light from the planet detectable. Doing so is a major technical challenge. All exoplanets that have been directly imaged are both large and widely separated from their parent star. Most of them are also very hot, so that they emit intense infrared radiation. The images have then been made at infrared where the planet is brighter than it is at visible wavelengths. During the gas accretion phase of giant planet formation, the star-planet contrast may be even better in H-alpha than it is in infrared. An H-alpha survey is currently underway. Specially designed direct imaging instruments such as Gemini Planet Imager, VLT Sphere, and SEXAO will image dozens of gas giants. However, the vast majority of known extrasolar planets have only been detected through indirect methods. The following are the indirect methods that have proven useful. Indirect methods. Transit method. If a planet crosses in front of its parent star's disk, then the observed brightness of the star drops by a small amount. The amount by which the star dims depends on its size and on the size of the planet, among other factors. This method suffers from a substantial rate of false positives, and confirmation from another method is usually considered necessary. The transit method reveals the radius of a planet, and it has the benefit that it sometimes allows a planet's atmosphere to be investigated through spectroscopy. Because the transit method requires that part of the planet's orbit intersect a line of sight between the host star and Earth, the probability that an exoplanet in a randomly oriented orbit will be observed to transit the star is somewhat small. Radial velocity or Doppler method: as a planet orbits a star, the star also moves in its own small orbit around the system's center of mass. Variations in the star's radial velocity that is, the speed with which it moves towards or away from Earth can be detected from displacements in the star's spectral lines due to the Doppler effect. Extremely small radial velocity variations can be observed, of 1 meter per second or even somewhat less. This method has the advantage of being applicable to stars with a wide range of characteristics. One of its disadvantages is that it cannot determine a planet's true mass, but can only set a lower limit on that mass. However, if the radial velocity of the planet itself can be distinguished from the radial velocity of the star, then the true mass can be determined. Transit timing variation: when multiple planets are present, each one slightly perturbs the other's orbits. Small variations in the times of transit for one planet can thus indicate the presence of another planet, which itself may or may not transit. For example, variations in the transits of the planet Kepler 19b suggest the existence of a second planet in the system, the non-transiting Kepler 19c. If multiple transiting planets exist in one system, then this method can be used to confirm their existence. In another form of the method, timing the eclipses in an eclipsing binary star can reveal an outer planet that orbits both stars. As of August 2013, a few planets have been found in that way, with numerous planets confirmed with this method. Transit duration variation: when a planet orbits multiple stars or if the planet has moons, its transit time can significantly vary per transit. Although no new planets or moons have been discovered with this method, it is used to successfully confirm many transiting circumbinary planets. Gravitational microlensing: microlensing occurs when the gravitational field of a star acts like a lens, magnifying the light of a distant background star. Planets orbiting the lensing star can cause detectable anomalies in the magnification as it varies over time. Unlike most other methods which have detection bias towards planets with small orbits, microlensing method is most sensitive to detecting planets around 1–10 AU away from Sun-like stars. Astrometry: astrometry consists of precisely measuring a star's position in the sky and observing the changes in the position over time. The motion of a star due to the gravitational influence of a planet may be observable. Because the motion is so small, however, this method has not yet been very productive. It has produced only a few disputed detections, though it has been successfully used to investigate the properties of planets found in other ways. Pulsar timing: a pulsar emits radio waves extremely regularly as it rotates. If planets orbit the pulsar, they will cause slight anomalies in the timing of its observed radio pulses. The first confirmed discovery of an extrasolar planet was made using this method. But as of 2011, it has not been very productive. 5 planets have been detected in this way, around 3 different pulsars. Variable star timing: like pulsars, there are some other types of stars which exhibit periodic activity. Deviations from the periodicity can sometimes be caused by a planet orbiting it. As of 2013, a few planets have been discovered with this method. Reflection emission modulations: when a planet orbits very close to the star, it catches a considerable amount of starlight. As the planet orbits around the star, the amount of light changes due to planets having phases from Earth's viewpoint, a planet glowing more from one side than the other due to temperature differences. Relativistic beaming: relativistic beaming measures the observed flux from the star due to its motion. The brightness of the star changes as the planet moves closer or further away from its host star. Ellipsoidal variations. Massive planets close to their host stars can slightly deform the shape of the star. This causes the brightness of the star to slightly deviate depending how it is rotated relative to Earth. Polarimetry. With polarimetry method, a polarized light reflected off the planet is separated from unpolarized light emitted from the star. No new planets have been discovered with this method, although a few already discovered planets have been detected with this method. Circumstellar disks. Disks of space dust surround many stars, believed to originate from collisions among asteroids and comets. The dust can be detected because it absorbs starlight and re-emits it as infrared radiation. Features in the disks may suggest the presence of planets, though this is not considered a definitive detection method. Space telescopes. Most confirmed extrasolar planets have been found using ground-based telescopes. However, many of the methods can work more effectively with space-based telescopes that avoid atmospheric haze and turbulence. CORO and Kepler were space missions dedicated to searching for extrasolar planets. Hubble Space Telescope and MOST have also found or confirmed a few planets. The Gaia mission, launched in December 2013, will use astrometry to determine the true masses of 1,000 nearby exoplanets. CHEOPS and TESS, to be launched in 2017, and Plato in 2024 will use the transit method. Primary and secondary detection, verification and falsification methods, verification by multiplicity, transit color signature, characterization methods, transmission spectroscopy, nomenclature, proper names. Most exoplanets have catalog names which are explained in the following sections, but in 2014 the IAU launched a process for giving proper names to exoplanets. The process involves public nomination and voting for the new names, and the IAU plans to announce the new names in August 2015. The decision to give the planets new names followed the private company Uwingu's exoplanet naming contest, which the IAU harshly criticized. Previously a few planets had received unofficial names, notably Osiris, Bellerophon, and Methuselah. Multiple Star Standard. The convention for naming exoplanets is an extension of the one used by the Washington Multiplicity Catalog for multiple star systems, and adopted by the International Astronomical Union. The brightest member of a star system receives the letter A. Distinct components not contained within A are labeled B, C, etc. Subcomponents are designated by one or more suffixes with the primary label, starting with lowercase letters for the second hierarchical level and then numbers for the third. For example, if there is a triple star system in which two stars orbit each other closely with a third star in a more distant orbit, the two closely orbiting stars would be named O and AB, whereas the distant star would named B. For historical reasons, this standard is not always followed. For example, Alpha Centauri, B and C are not labeled Alpha Centauri or AB and B. Extrasolar planet standard. Following an extension of the above standard, an exoplanet's name is normally formed by taking the name of its parent star and adding a lowercase letter. The first planet discovered in a system is given the designation B, and later planets are given subsequent letters. If several planets in the same system are discovered at the same time, the closest one to the star gets the next letter, followed by the other planets in order of orbital size. For instance, in the 55 Cancri system the first planet Euro 55 Cancri bar Euro was discovered in 1996. Two additional father planets were simultaneously discovered in 2002 with the nearest to the star being named 55 Cancri C and the other 55 Cancri D. A fourth planet was claimed in 2004 and named 55 Cancri E despite lying closer to the star than 55 Cancri B. And the most recently discovered planet, in 2007, was named 55 Cancri F despite lying between 55 Cancri C and 55 Cancri D. As of April 2012 the highest letter in use is J, for the unconfirmed planet HD 10180J, and with H being the highest letter for a confirmed planet, belonging to the same host star. If a planet orbits one member of a binary star system, then an uppercase letter for the star will be followed by a lowercase letter for the planet. Examples are 16 Cygni Bb and HD 178911 Bb. Planets orbiting the primary or A star should have AB after the name of the system, as in HD 41004 AB. However, the A is sometimes omitted. For example, the first planet discovered around the primary star of the Tau Boa paragraph Tis binary system is usually called simply Tau Boa paragraph Tis B. If the parent star is a single star, then it may still be regarded as having an A designation, though the A is not normally written. The first exoplanet found to be orbiting such a star could then be regarded as a secondary subcomponent that should be given the suffix AB. For example, 51 Peg-Or is the host star in the system 51 Peg. And the first exoplanet is then 51 Peg-Ab. Because most exoplanets are in single-star systems, the implicit A designation was simply dropped, leaving the exoplanet name with the lower-case letter only, 51 Peg-B. A few exoplanets have been given names that do not conform to the above standard. For example, the planets that orbit the pulsar PSA 1257 are often referred to with capital rather than lowercase letters. Also, the underlying name of the star system itself can follow several different systems. In fact, some stars have only received their names due to their inclusion in planet search programs, previously only being referred to by their celestial coordinates. Circumbinary Planets and 2010 Proposal, Hessman al. state that the implicit system for exoplanet names utterly failed with the discovery of circumbinary planets. They note that the discoverers of the two planets around HW Virginis tried to circumvent the naming problem by calling them HW3 and HW4, that is the latter as the fourth object Eurostellar or planetary discovered in the system. They also note that the discoverers of the two planets around NN Serpentis were confronted with multiple suggestions from various official sources and finally chose to use the designations NN Ser C and NN Ser D. The proposal of Hessman al. starts with the following two rules. Rule 1. The formal name of an exoplanet is obtained by appending the appropriate suffixes to the formal name of the host star or stellar system. The upper hierarchy is defined by uppercase letters, followed by lowercase letters, followed by numbers, etc. The naming order within a hierarchical level is for the order of discovery only. Rule 2. Whenever the leading capital letter designation is missing, this is interpreted as being an informal form with an implicit A unless otherwise explicitly stated. They note that under these two proposed rules all of the present names for 99% of the planets around single stars are preserved as informal forms of the IAU-sanctioned provisional standard. They would rename Tau Boa paragraph Tis B formally as Tau Boa paragraph Tis AB, retaining the prior form as an informal usage. To deal with the difficulties relating to circumbinary planets, the proposal contains two further rules. Rule 3. As an alternative to the nomenclature standard in Rule 1, a hierarchical relationship can be expressed by concatenating the names of the higher-order system and placing them in parentheses, after which the suffix for a lower-order system is added. Rule 4. When in doubt, the hierarchy expressed by the nomenclature should correspond to dynamically distinct systems in order of their dynamical relevance. The choice of hierarchical levels should be made to emphasize dynamical relationships, if known. They submit that the new form using parentheses is the best for known circumbinary planets and has the desirable effect of giving these planets identical sublevel hierarchical labels and stellar component names that conform to the usage for binary stars. They say that it requires the complete renaming of only two exoplanetary systems. The planets around HW Virginis would be renamed HW B and C, whereas those around NN Serpentis would be renamed NN Ser B and C. In addition, the previously known single circumbinary planets around PSA B 1620-26 and DP Linus, can almost retain their names as unofficial informal forms of the AB, B designation where the AB is left out. The discoverers of the circumbinary planet around Kepler 16 followed the naming scheme proposed by Hessman al. When naming the body Kepler 16b, or simply Kepler 16b when there is no ambiguity. Other naming systems, and other nomenclature, often seen in science fiction, uses Roman numerals in the order of planets' positions from the star. But such a system is impractical for scientific use, because new planets may be found closer to the star, changing all numerals. Formation and evolution. Initial conditions of planet formation, lifetimes of primordial disks, Eric E. Mamajk, June 26, 2009, on the formation timescale and core masses of gas giant planets, W. K. M. Rice, Philip J. Armitage, October 7, 2003, a short timescale for terrestrial planet formation from HFW chronometry of meteorites, Yin, Kantsu. Jacobson, S. B. Yamashita, K. Bleichert Toft, J. Tar Copyright Lauk, P. Olberada, F. Nature, Volume 418, Issue 6901, ppA 949 a 952, Origin and loss of nebula-captured hydrogen envelopes from sub- to super-Earths in the habitable zone of Sun-like stars, H. Lammer, A. Star Paragraph Kl, N. Vyerkov, Each Dorfy, P. Odert, M. Garwan Kortadel, UN. Kulikov, K. G. Kaisliakova, M. Lietzinger, January 13, 2014, Thermally Driven Atmospheric Escape, R. E. Johnson, February 7, 2010, Atmospheric Mass Loss by Stellar Wind from Planets Around Main Sequence M Stars, Jesus Sendjas, Antigona Segura, Alejandro Raga, May 31, 2010, Co-Evolution of Atmospheres, Life, and Climate, John Lee Grenfell et al., May 20, 2010, Phase Separation in Giant Planets, Inhomogeneous Evolution of Saturn, Jonathan J. Fortney, William B. Hubbard, May 1, 2003, Magnetodynamo Lifetimes for Rocky, Earth-mass exoplanets with contrasting mantle convection regimes, Joost van Summeren, Eric Guidos, Clinton P. Conrad. April 9, 2013, The Effect of Evaporation on the Evolution of Close-in Giant Planets, I. Barath, F. Celsus, G. Chabria, T. S. Barman, F. Allard, P. H. Horschilt, H. Lammer, April 5, 2004, Observational Evidence for Tidal Destruction of Exoplanets, Brian Jackson, Rory Barnes, Richard Greenberg, April 7, 2009, A Dying Universe, The Long-Term Fate and Evolution of Astrophysical Objects, Frederick C. Adams, Gregory Laughlin, January 18, 1997, Planet Hosting Stars. Proportion of stars with planets. Planet search programs have discovered planets orbiting a substantial fraction of the stars they have looked at. However, the overall proportion of stars with planets is uncertain because not all planets can yet be detected. The radial velocity method and the transit method are most sensitive to large planets in small orbits. Thus many known exoplanets are hot Jupiter's planets of Jovian mass or larger in very small orbits with periods of only a few days. A 2005 survey of radial velocity detected planets found that about 1.2% of Sun-like stars have a hot Jupiter, where Sun-like star refers to any main sequence star of spectral classes late F, G, or early K without a close stellar companion. This 1.2% is more than double the frequency of hot Jupiters detected by the Kepler spacecraft, which may be because the Kepler field of view covers a different region of the Milky Way where the metallicity of stars is different. It is further estimated that 3% to 4.5% of Sun-like stars possess a giant planet with an orbital period of 100 days or less, where giant planet means a planet of at least 30 Earth masses. It is known that small planets are more common than giant planets. It also appears that there are more planets in large orbits than in small orbits. Based on this, it is estimated that perhaps 20% of Sun-like stars have at least one giant planet whereas at least 40% may have planets of lower mass. A 2012 study of gravitational microlensing data collected between 2002 and 2007 concludes the proportion of stars with planets is much higher and estimates an average of 1.6 planets orbiting between 0.5 a 10 AU per star in the Milky Way. The authors of this study conclude that stars are orbited by planets as a rule, rather than the exception. In November 2013 it was announced that 22A plus or minus 8% of Sun-like stars have an Earth-sized planet in the habitable zone. Whatever the proportion of stars with planets, the total number of exoplanets must be very large. Because the Milky Way has at least 200 billion stars, it must also contain tens or hundreds of billions of planets. Spectral classification. Most known exoplanets orbit stars roughly similar to the Sun, that is, main sequence stars of spectral categories F, G, or K. One reason is that planet search programs have tended to concentrate on such stars. But in addition, statistical analysis indicates that lower mass stars are less likely to have planets massive enough to detect by the radial velocity method. Although several tens of planets around red dwarfs have been discovered by the Kepler spacecraft, which uses the transit method, which can detect smaller planets. Stars of spectral category A typically rotate very quickly, which makes it very difficult to measure the small Doppler shifts induced by orbiting planets because the spectral lines are very broad. However, this type of massive star eventually evolves into a cooler red giant that rotates more slowly and thus can be measured using the radial velocity method. A few tens of planets have been found around red giants. Observations using the Spitzer Space Telescope indicate that extremely massive stars of spectral category O, which are much hotter than the Sun, produce a photoevaporation effect that inhibits planetary formation. When the O-type star goes supernova, any planets that had formed would become free-floating due to the loss of stellar mass unless the natal kick of the resulting remnant pushes it in the same direction as an escaping planet. Doppler surveys around a wide variety of stars indicate about 1 in 6 stars having twice the mass of the Sun are orbited by one or more Jupiter-sized planets, versus 1 in 16 for Sun-like stars and only 1 in 50 for red dwarfs. On the other hand, microlensing surveys indicate that long-period Neptune-mass planets are found around 1 in 3 red dwarfs. Kepler Space Telescope observations of planets with up to 1-year periods show that occurrence rates of Earth to Neptune-sized planets around M, K, G, and F stars are successively higher towards cooler, less massive stars. Metallicity. Ordinary stars are composed mainly of the light elements hydrogen and helium. They also contain a small proportion of heavier elements, and this fraction is referred to as a star's metallicity, denoted mH, and expressed on a logarithmic scale where 0 is the Sun's metallicity. A 2012 study of the Kepler spacecraft data found that the smaller planets with radii smaller than that of Neptune were found around stars with metallicities in the range of 0.6 mH, plus 0.5, whereas the larger planets were found mostly around stars with metallicity at the higher end of this range. In this study, small planets occurred about 3 times as frequently as large planets around stars of metallicity greater than that of the Sun, but they occurred around 6 times as frequently for stars of metallicity less than that of the Sun. The lack of gas giants around low metallicity stars could be because the metallicity of protoplanetary disks affects how quickly planetary cores can form and whether they accrete a gaseous envelope before the gas dissipates. However, Kepler can only observe planets very close to their star, and the detected gas giants probably migrated from further out, so a decreased efficiency of migration in low metallicity disks could also partly explain these findings. It has also been shown that stars with planets are more likely to be deficient in lithium. Multiple stars. Most known planets orbit single stars, but some orbit one member of a binary star system, and several circumbinary planets have been discovered which orbit around both members of binary star. A few planets in triple star systems are known, and one in the quadruple system Kepler 64. The Kepler results indicate circumbinary planetary systems are relatively common. One puzzling finding is none of the close binary stars surveyed appear to have eclipsing planets. Half of the stars have an orbital period of 2.7 days or less, but none of the binaries with planets have a period less than 7.4 days. Another surprising Kepler finding is circumbinary planets tend to orbit their stars close to the critical instability radius. Open clusters. Most stars form in open clusters, but very few planets have been found in open clusters, and this led to the hypothesis that the open cluster environment hinders planet formation. However, a 2011 study concluded that there have been an insufficient number of surveys of clusters to make such a hypothesis. The lack of surveys was because there are relatively few suitable open clusters in the Milky Way. Recent discoveries of both giant planets and low-mass planets in open clusters are consistent with there being similar planet occurrence rates in open clusters as around field stars. The open cluster NGC 6811 contains two known planetary systems, Kepler 66 and Kepler 67. Captured planets, free-floating planets in open clusters have similar velocities to the stars and so can be recaptured. They are typically captured into wide orbits between 100 and 105 AU. The capture efficiency decreases with increasing cluster size, and for a given cluster size it increases with the host primary mass. It is almost independent of the planetary mass. Single and multiple planets could be captured into arbitrary unaligned orbits, non-coplanar with each other or with a stellar host spin, or pre-existing planetary system. Some planet-to-host metallicity correlation may still exist due to the common origin of the stars from the same cluster. Planets would be unlikely to be captured around neutron stars because these are likely to be ejected from the cluster by a pulsar kick when they form. Planets could even be captured around other planets to form free-floating planet binaries. After the cluster has dispersed, some of the captured planets with orbits larger than 106 AU would be slowly disrupted by the galactic tide and likely become free-floating again through encounters with other field stars or giant molecular clouds. Galactic distribution of planets. The Milky Way is 100,000 light-years across, but 90% of planets with known distances lie within about 2,000 light-years of Earth, as of July 2014. One method that can detect planets much further away is microlensing. The WFIRST spacecraft could use microlensing to measure the relative frequency of planets in the galactic bulge versus galactic disk. So far, the indications are that planets are more common in the disk than the bulge. Estimates of the distance of microlensing events is difficult. The first planet considered with high probability of being in the bulge is MOA 2011 BLG 293 pounds at a distance of 7.7 kilopascs. Population I, or metal-rich stars, are those young stars whose metallicity is highest. The high metallicity of population I stars makes them more likely to possess planetary systems than older populations, because planets form by the accretion of metals. The Sun is an example of a metal-rich star. These are common in the spiral arms of the Milky Way. Generally, the youngest stars, the extreme population I, are found farther in and intermediate population I stars are farther out, etc. The Sun is considered an intermediate population I star. Population I stars have regular elliptical orbits around the galactic center, with a low relative velocity. Population II, or metal-poor stars, are those with relatively low metallicity which can have hundreds or thousands times less metallicity than the Sun. These objects formed during an earlier time of the universe. Intermediate population II stars are common in the bulge near the center of the Milky Way, whereas population II stars found in the galactic halo are older and thus more metal-poor. Globular clusters also contain high numbers of population II stars. In 2014 the first planets around a halo star were discovered around Captain's star, the nearest halo star to Earth, around 13 light-years away. With an age greater than 10 billion years, the planet Captain B is the oldest known planet in a habitable zone. The metallicity of Captain's star is estimated to be about 8 times less than the Sun. Different types of galaxies have different histories of star formation and hence planet formation. Planet formation is affected by the ages, metallicities, and orbits of stellar populations within a galaxy and vary between the different types of galaxies. The distribution of the different types of galaxies in the universe depends on their location within galaxy clusters. Age, the ages of stars, David A. Soderblom, March 31, 2010, towards asteroseismically calibrated age rotation activity relations for Kepler solar-like stars, R. A. Garcia al. March 27, 2014, accurate parameters of the oldest known rocky exoplanet hosting system, Kepler 10 revisited, Alexandra Vogtman-Schultz al. December 5, 2013, Asteroseismology, the importance of asteroseismology in exoplanetary science, F. Borsa, E. Peretti, Set Ots Astroit, what asteroseismology can do for exoplanets, Kepler 410ab is a small Neptune around a bright star, in an eccentric orbit consistent with low obliquity. Vincent van Allen al. December 17, 2013, Pulsations and Planets, The Asteroseismology Extrasolar Planet Connection, Sonia School, May 19, 2010, Stellar Activity, How Stellar Activity Affects the Size Estimates of Extrasolar Planets, S. Schaller, K. F. Huber, U. Walter, S. Paragrafter, J. H. M. M. Schmidt, June 19, 2009, Hot Jupiters and Stellar Magnetic Activity, A. F. Lanza, May 20, 2008, Extrasolar Giant Planets and X-ray Activity, Vinay L. Kashyap, Jeremy J. Drake, Stephen H. Saar, July 21, 2008, Mass Loss of Hot Jupiters Implications for Corot Discoveries. Part 1, The Importance of Magnetospheric Protection of a Planet Against Ion Loss Caused by Coronal Mass Ejections, Kudlikenko al. April 2007, Orbital Parameters. Most known extrasolar planet candidates have been discovered using indirect methods and therefore only some of their physical and orbital parameters can be determined. For example, out of the 6 independent parameters that define an orbit, the radial velocity method can determine 4, semi-major axis, eccentricity, longitude of periastron, and time of periastron. 2 parameters remain unknown, inclination and longitude of the ascending node. Distance from star, semi-major axis and orbital period. The orbit of a planet is not centered on the star but on their common center of mass. For circular orbits, the semi-major axis is the distance between the planet and the center of mass of the system. For elliptical orbits, the planet-to-star distance varies over the course of the orbit, in which case the semi-major axis is the average of the largest and smallest distances between the planet and the center of mass of the system. If the sizes of the star and planet are relatively small compared to the size of the orbit and the orbit is nearly circular and the center of mass is not too far from the star's center, such as in the Earth-Sun system, then the distance from any point on the star to any point on the planet is approximately the same as the semi-major axis. However, when a star's radius expands when it turns into a red giant, then the distance between the planet and the star's surface can become close to zero, or even less than zero if the planet has been engulfed by the expanding red giant, whereas the center of mass from which the semi-major axis is measured will still be near the center of the red giant. Orbital period is the time taken to complete one orbit. For any given star, the shorter the semi-major axis of a planet, the shorter the orbital period. Also comparing planets around different stars but with the same semi-major axis, the more massive the star, the shorter the orbital period. There are exoplanets that are much closer to their parent star than any planet in the solar system is to the Sun, and there are also exoplanets that are much further from their star. Mercury, the closest planet to the Sun at 0.4 AU, takes 88 days for an orbit, but the shortest known orbits for exoplanets take only a few hours, for example Kepler 70b. The Kepler 11 system has 5 of its planets in shorter orbits than Mercury. Neptune is 30 AU from the Sun and takes 165 years to orbit, but there are exoplanets that are hundreds of AU from their star and take more than 1,000 years to orbit, for example Warner XS 1609b. Over the lifetime of a star, the semi-major axis of his planets changes. This planetary migration happens especially during the formation of the planetary system when planets interact with the protoplanetary disk and each other until a relatively stable position is reached, and later in the red giant and asymptotic giant branch phases when the star expands and engulfs the nearest planets that can cause them to move inwards, and when the giant phases lose mass as the outer layers dissipate causing planets to move outwards as a result of the star's reduced gravitational field. The radial velocity and transit methods are most sensitive to planets with small orbits. The earliest discoveries such as 51 Peg-b were gas giants with orbits of a few days. These hot Jupiters likely formed further out and migrated inwards. The Kepler spacecraft has found planets with even shorter orbits of only a few hours, which places them within the star's upper atmosphere or corona, and these planets are Earth-sized or smaller and are probably the leftover solid cores of giant planets that have evaporated due to being so close to the star, or even being engulfed by the star in its red giant phase in the case of Kepler 70b. As well as evaporation, other reasons why larger planets are unlikely to survive orbits only a few hours long include orbital decay caused by tidal force, tidal inflation instability, and Roche lobe overflow. The Roche limit implies that small planets with orbits of a few hours are likely made mostly of iron. The direct imaging method is most sensitive to planets with large orbits, and has discovered some planets that have planet-to-Eurostar separations of hundreds of AU. However, protoplanetary disks are usually only around 100 AU in radius, and core accretion models predict giant planet formation to be within 10 AU, where the planets can coalesce quickly enough before the disk evaporates. Very long-period giant planets may have been free-floating planets that were captured, or formed close-in and gravitationally scattered outwards, or the planet and star could be a mass-imbalanced Y-binary system with the planet being the primary object of its own separate protoplanetary disk. Gravitational instability models might produce planets at multi-hundred AU separations, but this would require unusually large disks. For planets with very wide orbits up to several 100,000 AU, it may be difficult to observationally determine whether the planet is gravitationally bound to the star. Most planets that have been discovered are within a couple of AU of their star because the most used methods require observation of several orbits to confirm that the planet exists, and there has only been enough time since these methods were first used to cover small separations. Some planets with larger orbits have been discovered by direct imaging, but there is a middle range of distances, roughly equivalent to the Solar System's gas giant region, which is largely unexplored. Direct imaging equipment for exploring that region is being installed on the world's largest telescopes and should begin operation in 2014. For example, Gemini Planet Imager and VLT Sphere. The microlensing method has detected a few planets in the 1-10 AU range. It appears plausible that in most exoplanetary systems, there are one or two giant planets with orbits comparable in size to those of Jupiter and Saturn in the Solar System. Giant planets with substantially larger orbits are now known to be rare, at least around Sun-like stars. The distance of the habitable zone from a star depends on the type of star, and this distance changes during the star's lifetime as the size and temperature of the star changes. Eccentricity. The eccentricity of an orbit is a measure of how elliptical it is. All the planets of the Solar System except for Mercury have near-circular orbits. Most exoplanets with orbital periods of 20 days or less have near-circular orbits, that is very low eccentricity. That is believed to be due to tidal circularization, reduction of eccentricity over time due to gravitational interaction between two bodies. The mostly sub-Neptune-sized planets found by the Kepler spacecraft with short orbital periods have very circular orbits. By contrast, the giant planets with longer orbital periods discovered by radial velocity methods have quite eccentric orbits. Moderate to high eccentricities of giant planets are not an observational selection effect, because a planet can be detected about equally well regardless of the eccentricity of its orbit. The prevalence of elliptical orbits for giant planets is a major puzzle, because current theories of planetary formation strongly suggest planets should form with circular orbits. However, for weak Doppler signals near the limits of the current detection ability, the eccentricity becomes poorly constrained and biased towards higher values. It is suggested that some of the high eccentricities reported for low-mass exoplanets may be overestimates, because simulations show that many observations are also consistent with two planets on circular orbits. Reported observations of single planets in moderately eccentric orbits have about a 15% chance of being a pair of planets. This misinterpretation is especially likely if the two planets orbit with a 2-1 resonance. With the exoplanet sample known in 2009, a group of astronomers has concluded that, 1, around 35% of the published eccentric 1-planet solutions are statistically indistinguishable from planetary systems in 2-1 orbital resonance, another 40% cannot be statistically distinguished from a circular orbital solution, and, 3, planets with masses comparable to Earth could be hidden in known orbital solutions of eccentric super-Earths and Neptune-mass planets. Radial velocity surveys found exoplanet orbits beyond 0.1 AU to be eccentric, particularly for large planets. Kepler spacecraft transit data is consistent with ERV surveys and also revealed that smaller planets tend to have less eccentric orbits. Eccentricity dynamics. High orbital eccentricities of extrasolar planets induced by the Kozai mechanism, G to Kada, FA ratio, last revised June 9, 2005, extreme climate variations from Milankovitch-like eccentricity oscillations in extrasolar planetary systems, David S. Spiegel, October 11, 2010, Orbital Dynamics of Multi-Planet Systems with Eccentricity Diversity, Stephen A. Kane, Sean N. Raymond, February 8, 2014, Type II Migration of Planets on Eccentric Orbits, Althea V. Muirhead, Eric B. Ford, April 21, 2009, Inclination versus Spin Orbit Angle. Orbital inclination is the angle between a planet's orbital plane and another plane of reference. For exoplanets, the inclination is usually stated with respect to an observer on Earth. The angle used is that between the normal to the planet's orbital plane and the line of sight from Earth to the star. Therefore, most planets observed by the transit method are close to 90 degrees. Since the word inclination is used in exoplanet studies for this line of sight inclination, then the angle between the planet's orbit and the star's rotation must use a different word and is termed the spin-orbit angle or spin-orbit alignment. In most cases, the orientation of the star's rotational axis is unknown. The Kepler spacecraft has found a few hundred multi-planet systems, and in most of these systems the planets all orbit in nearly the same plane, much like the Solar System. However, a combination of astrometric and radial velocity measurements has shown that some planetary systems contain planets whose orbital planes are significantly tilted relative to each other. More than half of hot Jupiters have orbital planes substantially misaligned with their parent star's rotation. A substantial fraction of hot Jupiters even have retrograde orbits, meaning that they orbit in the opposite direction from the star's rotation. Rather than a planet's orbit having been disturbed, it may be that the star itself flipped early in their system's formation due to interactions between the star's magnetic field and the planet-forming disk. Inclination dynamics, a window on exoplanet dynamical histories, Rossiter McLaughlin observations of WASP-13b and WASP-32b, R. D. Brothwell al. March 17, 2014, Periastron precession, cyclic transit probabilities of long-period eccentric planets due to periastron precession, Stephen A. Kane, Jonathan Horner, Caspar von Braun, September 7, 2012, observability of the general relativistic precession of periastra in exoplanets, Andres Jordan, Gaspar A. Barkos, June 3, 2008, nodal precession, classical and relativistic node precessional effects in WASP-33b and perspectives for detecting them, Lorenzo Orio, August 25, 2010, rotation and axial tilt. In April 2014, the first measurement of a planet's rotation period was announced. The length of day for the super-Jupiter gas giant Beta Pictoris b is 8 hours with an equatorial rotational velocity of 25 km per second. This spin is faster than the gas giants of the Solar System, in line with expectation that the more mass a gas giant has, the faster it spins. Beta Pictoris b's distance from its star is 9 AU. At such distances, the rotation of Jovian planets is not slowed by tidal effects. Beta Pictoris b is still warm and young, and over the next hundreds of millions of years, it will cool down and shrink to about the size of Jupiter, and if its angular momentum is preserved, then as it shrinks the length of its day will decrease to about 3 hours and its equatorial rotation velocity will speed up to about 40 km per second. The images of Beta Pictoris b do not have high enough resolution to directly see details, but Doppler spectroscopy techniques were used to show that different parts of the planet were moving at different speeds and in opposite directions, from which it was inferred that the planet is rotating. With the next generation of large ground-based telescopes, it will be possible to use Doppler imaging techniques to make a global map of the planet, like the recent mapping of the brown dwarf Lumen 16b. Origin of spin and tilt of terrestrial planets. Giant impacts have a large effect on the spin of terrestrial planets. The last few giant impacts during planetary formation tend to be the main determiner of a terrestrial planet's rotation rate. On average, the spin angular velocity will be about 70% of the velocity that would cause the planet to break up and fly apart. The natural outcome of planetary embryo impacts at speeds slightly larger than escape velocity. In later stages, terrestrial planet spin is also affected by impacts with planetesimals. During the giant impact stage, the thickness of a protoplanetary disk is far larger than the size of planetary embryos, so collisions are equally likely to come from any direction in 3 dimensions. This results in the axial tilt of accreted planets ranging from 0 to 180 degrees, with any direction as likely as any other, with both prograde and retrograde spins equally probable. Therefore, prograde spin with small axial tilt, common for the Solar System's terrestrial planets except for Venus, is not common in general for terrestrial planets built by giant impacts. The initial axial tilt of a planet determined by giant impacts can be substantially changed by stellar tides if the planet is close to its star, and by satellite tides if the planet has a large satellite. Tidal effects: for most planets the rotation period and axial tilt are not known, but a large number of planets have been detected with very short orbits and will probably have reached an equilibrium rotation that can be predicted. Tidal effects are the result of forces acting on a body differing from one part of the body to another. For example, the gravitational effect of a star varies with distance from one side of a planet to another. Also, heat from a star creates a temperature gradient between the day and night sides, which is another source of tides. For example, on Earth, air pressure variations on the ground are affected more by temperature differences than gravitational ones. Tides modify the rotation and orbit of planets until an equilibrium is reached. Whenever the rotation rate is slowed, there is an increase of the orbit's semi-major axis due to the conservation of angular momentum. Most of the large moons in the Solar System, including the Moon, are tidally locked to their host planet. The same side of the Moon is always facing the planet. This means the Moon's rotation periods are synchronous with their orbital period. However, when an orbit is eccentric, as is the case with many exoplanets' orbits of their host stars, there are equilibrium states such as spin-orbit resonances that are far more likely than synchronous rotation. A spin-orbit resonance is when the rotation period and the orbital period are in an integer ratio. This is called a commensurability. Non-resonant equilibriums such as the retrograde rotation of Venus can also occur when both gravitational and thermal atmospheric tides are both significant. A synchronous tidal lock isn't necessarily particularly slow. There are planets with orbits that take only a few hours. Gravitational tides tend to reduce the axial tilt to zero, but over a longer time scale than the rotation rate reaches equilibrium. However, the presence of multiple planets in a system can cause axial tilt to be captured in a resonance called a Cassini state. There are small oscillations around this state, and in the case of Mars these axial tilt variations are chaotic. Hot Jupiter's close proximity to their host star means that their spin-orbit evolution is mostly due to the star's gravity and not the other effects. Hot Jupiter's rotation rate is not thought to be captured into spin-orbit resonance due to way fluid body reacts to tides, and therefore slows down to synchronous rotation if it is on a circular orbit, or slows to a non-synchronous rotation if on an eccentric orbit. Hot Jupiters are likely to evolve towards zero axial tilt even if they had been in a Cassini state during planetary migration when they were further from their star. Hot Jupiter's orbits will become more circular over time. However, the presence of other planets in the system on eccentric orbits, even ones as small as Earth and as far away as the habitable zone, can continue to maintain the eccentricity of the hot Jupiter so that the length of time for tidal circularization can be billions instead of millions of years. The rotation rate of planet HD 80606b is predicted to be about 1.9 days. HD 80606b avoids spin-orbit resonance because it is a gas giant. The eccentricity of its orbit means that it avoids becoming tidally locked. The super-Earth Gliese 581d would most probably be in a spin-orbit resonance of 2-1, performing 2 rotations about its axis during each orbit of its parent star. Therefore, the day on Gliese 581d should approximately be 67 Earth-1 registered trademark S days long. The second likeliest resonant state for that planet is 3-2. Physical parameters. Mass. When a planet is found by the radial velocity method, Its orbital inclination is unknown and can range from 0 to 90 degrees. The method is unable to determine the true mass of the planet, but rather gives a lower limit for its mass, n. In a few cases an apparent exoplanet may be a more massive object such as a brown dwarf or red dwarf. However, the probability of a small value of I is relatively low /2 per mil 13%, and hence most planets will have true masses fairly close to the observed lower limit. If a planet's orbit is nearly perpendicular to the line of vision, a planet can be detected through the transit method. The inclination will then be known, and the inclination combined with mass n from radial velocity will give the planet's true mass. Also, astrometric observations and dynamical considerations in multiple planet systems can sometimes provide an upper limit to the planet's true mass. The mass of a transiting exoplanet can also be determined from the transmission spectrum of its atmosphere, as it can be used to constrain independently the atmospheric composition, temperature, pressure, and scale height. Transit timing variation can also be used to find planets' masses, radius, density and bulk composition. Prior to recent results from the Kepler spacecraft, most confirmed planets were gas giants comparable in size to Jupiter or larger because they are most easily detected. However, the planets detected by Kepler are mostly between the size of Neptune and the size of Earth. If a planet is detectable by both the radial velocity and the transit methods, then both its true mass and its radius can be found. The planet's density can then be calculated. Planets with low density are inferred to be composed mainly of hydrogen and helium, whereas planets of intermediate density are inferred to have water as a major constituent. A planet of high density is inferred to be rocky, like Earth and the other terrestrial planets of the Solar System. Gas giants. Gaseous planets that are hot because they are close to their star or because they are still hot from their formation are expanded by the heat. For colder gas planets there is a maximum radius which is slightly larger than Jupiter, which occurs when the mass reaches a few Jupiter masses. Adding mass beyond this point causes the radius to shrink. Even when taking heating from the star into account, many transiting exoplanets are much larger than expected given their mass, meaning that they have surprisingly low density. See the magnetic field section for one possible explanation. Super-Earths, mini-Neptunes, and gas dwarfs. If a planet has a radius and/or mass between that of Earth and Neptune, then there is a question about whether the planet is rocky like Earth, a mixture of volatiles and gas like Neptune, a small planet with a hydrogen-helium envelope, or some other composition. Some of the Kepler transiting planets with radii in the range 1 to 4 Earth radii have had their masses measured by radial velocity or transit timing methods. The calculated densities show that up to 1.5 Earth radii these planets are rocky, and that density increases with increasing radius due to gravitational compression. However, between 1.5 and 4 Earth radii the density decreases with increasing radius. This indicates that above 1.5 Earth radii planets tend to have increasing amounts of volatiles and gas. Despite this general trend, there is a wide range of masses at a given radius, which could be because gas planets can have rocky cores of different masses or compositions, and could also be due to photoevaporation of volatiles. Thermal evolutionary atmosphere models suggest a radius of 1.75 times that of Earth as a dividing line between rocky and gaseous planets. Excluding close-in planets that have lost their gas envelope due to stellar irradiation, studies of the metallicity of stars suggest a dividing line of 1.7 Earth radii between rocky planets and gas dwarfs. Then another dividing line at 3.9 Earth radii between gas dwarfs and gas giants. These dividing lines are statistical trends and do not necessarily apply to specific planets because there are many other factors besides metallicity that affect planet formation, including distance from star. There may be larger rocky planets formed at larger distances. The discovery of the low-density Earth mass planet KOI 314c shows that there is an overlapping range of masses in which both rocky planets and low-density planets occur. Low-mass low-density planets could be ocean planets or super-Earths with a remnant hydrogen atmosphere, or hot planets with a steam atmosphere, or mini-Neptunes with a hydrogen-helium atmosphere. Other possibilities for low-mass low-density planets are large atmospheres of carbon monoxide, carbon dioxide, methane, or nitrogen. Massive solid planets. In 2014, new measurements of Kepler 10c found that it was a Neptune-mass planet with a density higher than the Earth, indicating that Kepler 10c is made mostly of rock with possibly up to 20% high-pressure water ice but without a hydrogen-dominated envelope. As it is well above the 10 Earth mass upper limit that is commonly used for the term super-Earth, the term mega-Earth has been proposed. A similarly massive and dense planet could be Kepler 131b, although its density is not as well measured as Kepler 10c. The next most massive known solid planets are half this mass, 55 Cancri and Kepler 20b. Gas planets can also have large solid cores. The Saturn mass planet HD 149026b has only two-thirds of Saturn's radius, so may have a rock-ice core of 60 Earth masses or more. Transit timing variation measurements indicate that Kepler 52b, Kepler 52c and Kepler 57b have maximum masses between 30 and 100 times the mass of the Earth, although the actual masses could be much lower. With radii about 2 Earth radii in size, they might have densities larger than an iron planet of the same size. They orbit very close to their stars, so they could be the remnant cores of evaporated gas giants or brown dwarfs. If cores are massive enough, they could remain compressed for billions of years despite losing the atmospheric mass. Solid planets up to thousands of Earth masses may be able to form around massive stars, where the protoplanetary disk would contain enough heavy elements. Also, these stars have high UV radiation and winds that could photo-evaporate the gas in the disk, leaving just the heavy elements. For comparison, Neptune's mass equals 17 Earth masses, Jupiter has 318 Earth masses, and the 13 Jupiter mass limit used in the IAU's working definition of an exoplanet equals approximately 4,000 Earth masses. Another way of forming massive solid planets is when a white dwarf in a close binary system loses material to a companion neutron star. The white dwarf can be reduced to planetary mass, leaving just its crystallized carbon-oxygen core. A likely example of this is PSJ 1719-1438b. Cold planets have a maximum radius because adding more mass at that point causes the planet to compress under the weight instead of increasing the radius. The maximum radius for solid planets is smaller than the maximum radius for gas planets. Shape: when the size of a planet is described using its radius, this is approximating the shape by a sphere. However, the rotation of a planet causes it to be flattened at the poles so that the equatorial radius is larger than the polar radius, making it closer to an oblate spheroid. The oblateness of transiting exoplanets will affect the transit light curves. At the limits of current technology, it has been possible to show that HD 189733b is less oblate than Saturn. If the planet is close to its star, then gravitational tides will elongate the planet in the direction of the star, so that the planet will be closer to a triaxial ellipsoid. Because tidal deformation is along a line between the planet and the star, it is difficult to detect from transit photometry. It will have an order of magnitude less effect on the transit light curves than that caused by rotational deformation, even in cases where the tidal deformation is larger than rotational deformation. Material rigidity of rocky planets and rocky cores of gas planets will cause further deviations from the aforementioned shapes. Thermal tides caused by unevenly irradiated surfaces are another factor. Atmosphere. As of February 2014, more than 50 transiting and 5 directly imaged exoplanet atmospheres have been observed, resulting in detection of molecular spectral features. Observation of day-night temperature gradients and constraints on vertical atmospheric structure. Also, an atmosphere has been detected on the non-transiting hot Jupiter Tau Boa paragraph TIS-B. Spectroscopic measurements can be used to study a transiting planet's atmospheric composition, temperature, pressure, and scale height, and hence can be used to determine its mass. Stellar light is polarized by atmospheric molecules. This could be detected with a polarimeter. HD 189733b has been studied by polarimetry. Extrasolar planets have phases similar to the phases of the Moon. By observing the exact variation of brightness with phase, astronomers can calculate atmospheric particle sizes. Atmospheric composition. In 2001, sodium was detected in the atmosphere of HD 209,458b. In 2008, water, carbon monoxide, carbon dioxide and methane were detected in the atmosphere of HD 189,733b. In 2013, water was detected in the atmospheres of HD 209,458b, XO1b, WASP-12b, WASP-17b, and WASP-19b. In July 2014, NASA announced finding very dry atmospheres on 3 exoplanets orbiting Sun-like stars. The presence of oxygen may be detectable by ground-based telescopes, which, if discovered, would suggest the presence of life on an exoplanet. Atmospheric circulation. The atmospheric circulation of planets that rotate more slowly or have a thicker atmosphere allows more heat to flow to the poles, which reduces the temperature differences between the poles and the equator. Clouds. In October 2013, the detection of clouds in the atmosphere of Kepler 7b was announced, and, in December 2013, also in the atmospheres of GJ 436b and GJ 1214b. Precipitation. Precipitation in the form of liquid or solid varies in composition depending on atmospheric temperature, pressure, composition, and altitude. Hot atmospheres could have iron rain, molten glass rain, and rain made from rocky minerals such as instatite, corundum, spinel, and wollastonite. Deep in the atmospheres of gas giants it could rain diamonds and helium containing dissolved neon. Abiotic oxygen. The processes of life result in a mixture of chemicals that are not in chemical equilibrium, but there are also abiotic disequilibrium processes that need to be considered. The most robust atmospheric biosignature is often considered to be molecular oxygen O2 and its photochemical byproduct ozone O3. The photolysis of water H2O by UV rays followed by hydrodynamic escape of hydrogen can lead to a buildup of oxygen in planets close to their star undergoing runaway greenhouse effect. For planets in the habitable zone, it was believed that water photolysis would be strongly limited by cold trapping of water vapor in the lower atmosphere. However, the extent of H2O cold trapping depends strongly on the amount of non-condensable gases in the atmosphere such as nitrogen N2 and argon. In the absence of such gases, the likelihood of buildup of oxygen also depends in complex ways on the planet. Unregistered trademark accretion history, internal chemistry, atmospheric dynamics and orbital state. Therefore, oxygen on its own cannot be considered a robust biosignature. The ratio of nitrogen and argon to oxygen could be detected by studying thermal phase curves or by transit transmission spectroscopy measurement of the spectral Rayleigh scattering slope in a clear sky atmosphere. Climate and weather. Patterns of sunlight on extrasolar planets. Tony Dobrowolski's, March 18, 2014, Possible climates on terrestrial exoplanets, François Forget, Jeremy LeConte, November 18, 2013. Indication of insensitivity of planetary weathering behavior and habitable zone to surface land fraction, Dorian S. Abbott, Nicholas B. Cowan, Frederick J. Schessler, August 8, 2012, Clouds and Hazes in Exoplanet Atmospheres, Mark S. Marley, Andrew S. Ackerman, Jeffrey N. Cuzzy, Daniel Kitzman, January 23, 2013, Meteorology, Atmospheric Circulation of Exoplanets, Adam B. Showman, James Y. K. Cho, Chris and Menno, November 16, 2009, New technique could measure exoplanet atmospheric pressure, an indicator of habitability, Shannon Hall on March 6, 2014, www.universaturday.com, Surface composition. Surface features can be distinguished from atmospheric features by comparing emission and reflection spectroscopy with transmission spectroscopy. Mid-infrared spectroscopy of exoplanets may detect rocky surfaces, and near-infrared may identify magma oceans or high-temperature lavas, hydrated silicate surfaces and water ice, giving an unambiguous method to distinguish between rocky and gaseous exoplanets. Surface temperature. One can estimate the temperature of an exoplanet based on the intensity of the light it receives from its parent star. For example, the planet Ogle 2005 BLG 390 pounds is estimated to have a surface temperature of roughly a 220 degrees Celsius. However, such estimates may be substantially in error because they depend on the planet's usually unknown albedo, and because factors such as the greenhouse effect may introduce unknown complications. A few planets have had their temperature measured by observing the variation in infrared radiation as the planet moves around in its orbit and is eclipsed by its parent star. For example, the planet HD 189733b has been found to have an average temperature of 1205 A plus or minus 9 kelvins on its day side and 973 A plus or minus 33 K on its night side. Surface mapping, global mapping of Earth-like exoplanets from scattered light curves, Hoang Kohara, Yuko Fuya, July 16, 2010. A two-dimensional infrared map of the extrasolar planet HD 189733b, C. Magyar, Eagle, N. Cowan, September 19, 2012. Water. Water, From Clouds to Planets, B. Wynne F. Vandershok, Edwin A. Bergeon, Darius C. Lees, Jonathan Ilunin, February 25, 2014, Are exoplanets orbiting red dwarf stars too dry for life? Michael Sherber, Astrobiology Magazine, August 27, 2013, Carbon-rich exoplanets may lack surface water, October 26, 2013, Water-trapped worlds, Adam Hadezi, Astrobiology Magazine, 0713, Lobster-shaped extrasolar oceans, 0314, Charles Q. Choi, Astrobiology Magazine, Alien moons could bake dry from young gas giants' hot glow, Adam Hadezi, Astrobiology Magazine March 25, 2014, The Longevity of Oceans on Terrestrial Exoplanets, Bullock, Mark Allen. Grinspoon, D.H., False Positive for Ocean Glint on Exoplanets, The Latitude Albedo Effect, Nicholas B. Cowan, Dorian S. Abbott, Iko Voigt, May 4, 2012, General Features, Color and Brightness. In 2013 the color of an exoplanet was found for the first time. The best fit albedo measurements of HD 189733b suggest that it is deep dark blue. The darkest planet discovered is TRES-2b, a hot Jupiter, which reflects less than 1% of the light from its star, making it darker than coal or black acrylic paint. Hot Jupiters are expected to be quite dark due to sodium and potassium in their atmospheres, but it is not known why TRES-2b is so dark. It could be due to an unknown chemical. TRES-2b does emit a faint red glow because it is so hot. Magnetic field. Interaction between a close-in planet's magnetic field and a star can produce spots on the star in a similar way to how the Galilean moons produce aurorae on Jupiter. Auroral radio emissions could be detected with radio telescopes such as LOFAR. The radio emissions could enable determination of the rotation rate of a planet, which is difficult to detect otherwise. Earth's magnetic field results from its flowing liquid metallic core, but in super-Earths the mass can produce high pressures with large viscosities and high melting temperatures, which could prevent the interiors from separating into different layers and so result in undifferentiated coreless mantles. Magnesium oxide, which is rocky on Earth, can be a liquid metal at the pressures and temperatures found in super-Earths and could generate a magnetic field in the mantles of super-Earths. Hot Jupiters have been observed to have a larger radius than expected. This could be caused by the interaction between the stellar wind and the planet's magnetosphere, creating an electric current through the planet that heats it up, causing it to expand. The more magnetically active a star is, the greater the stellar wind and the larger the electric current, leading to more heating and expansion of the planet. This theory matches the observation that stellar activity is correlated with inflated planetary radii. Plate tectonics. On Earth-sized planets, plate tectonics is more likely if there are oceans of water. However, in 2007 two independent teams of researchers came to opposing conclusions about the likelihood of plate tectonics on larger super-Earths, with one team saying that plate tectonics would be episodic or stagnant and the other team saying that plate tectonics is very likely on super-Earths even if the planet is dry. If super-Earths have more than 80 times as much water as Earth, then they become ocean planets with all land completely submerged. However, if there is less water than this limit, then the deep water cycle will move enough water between the oceans and mantle to allow continents to exist. Rings. The star 1SWASPJ 140,747.93-394,542.6 is orbited by an object that is circled by a ring system much larger than Saturn's rings. However, the mass of the object is not known. It could be a brown dwarf or low-mass star instead of a planet. The brightness of optical images of Fomalhaut B could be due to starlight reflecting off a circumplanetary ring system with a radius between 20 to 40 times that of Jupiter's radius, about the size of the orbits of the Galilean moons. The rings of the solar system's gas giants are aligned with their planet's equator. However, for exoplanets that orbit close to their star, tidal forces from the star would lead to the outermost rings of a planet being aligned with the planet's orbital plane around the star. A planet's innermost rings would still be aligned with the planet's equator, so that if the planet has a tilted rotational axis, then the different alignments between the inner and outer rings would create a warped ring system. Moons. In December 2013, a candidate exomoon of a free-floating planet was announced. Comet-like tails, KIC 12,557,548b is a small rocky planet, very close to its star, that is evaporating and leaving a trailing tail of cloud and dust like a comet. The dust could be ash erupting from volcanoes and escaping due to the small planet's low surface gravity, or it could be from metals that are vaporized by the high temperatures of being so close to the star, with the metal vapor then condensing into dust. Volcanism. Detecting volcanism on extrasolar planets, L. Kaltenegger, W.G. Henning, D.D. Sasilov, September 7, 2010. Detecting planetary geochemical cycles on exoplanets, atmospheric signatures in the case of SO2, L. Kaltenegger, D. Sasilov, November 17, 2009, Geodynamics and Rate of Volcanism on Massive Earth-like Planets, Edwin S. Kite, Michael Manger, Eric Guidos, May 31, 2009, Tidal Heating of Terrestrial Extrasolar Planets and Implications for Their Habitability, Brian Jackson, Rory Barnes, Richard Greenberg, August 20, 2008, Interior Structure, Planetary Internal Structures, I. Barath, G. Chabria, J. Fortney, C. Sotin, January 19, 2014, Habitability. Habitable Zone. The habitable zone around a star is the region where the temperature is just right to allow liquid water to exist on a planet. That is, not too close to the star for the water to evaporate and not too far away from the star for the water to freeze. The heat produced by stars varies depending on the size and age of the star, so that the habitable zone can be at different distances. Also, the atmospheric conditions on the planet influence the planet's ability to retain heat, so that the location of the habitable zone is also specific to each type of planet. Desert planets, with very little water, will have less water vapor in the atmosphere than Earth and so have a reduced greenhouse effect, meaning that a desert planet could maintain oases of water closer to its star than Earth is to the Sun. The lack of water also means there is less ice to reflect heat into space, so the outer edge of desert planet habitable zones is further out. Rocky planets with a thick hydrogen atmosphere could maintain surface water much further out than the Earth-Sun distance. Habitable zones have usually been defined in terms of surface temperature, however over half of Earth's biomass is from subsurface microbes, and the temperature increases as you go deeper underground, so the subsurface can be habitable when the surface is frozen, and if this is considered then the habitable zone extends much further from the star. Even rogue planets could have liquid water at sufficient depths underground. In an earlier era of the universe, the temperature of the cosmic microwave background would allow any rocky planets that existed to have liquid water on their surface regardless of their distance from a star. Jupiter-like planets might not be habitable, but they could have habitable moons. Strong dependence of the inner edge of the habitable zone on planetary rotation rate. Junior Yang, Gwynal Bu, Daniel C. Fabricki, Dorian S. Abbott, April 19, 2014. Habitable zones around main sequence stars, dependence on planetary mass. Ravi Kumar Kopparapu, Ramses M. Ramirez, James Shuttlecott, James F. Casting, Sean Donegal Goldman, Vincent Amott, April 21, 2014, Ice Ages and Snowball States. The outer edge of the habitable zone is where planets will be completely frozen, but even planets well inside the HZ can periodically become frozen. If orbital fluctuations or other causes produce cooling, then this creates more ice, but ice reflects sunlight, causing even more cooling, creating a feedback loop until the planet is completely or nearly completely frozen. When the surface is frozen, this stops carbon dioxide weathering, resulting in a buildup of carbon dioxide in the atmosphere from volcanic emissions. This creates a greenhouse effect which unfreezes the planet again. Planets with a large axial tilt are less likely to enter snowball states and can retain liquid water further from their star. Large fluctuations of axial tilt can have even more of a warming effect than a fixed large tilt. Paradoxically, planets around cooler stars, such as red dwarfs, are less likely to enter snowball states because the infrared radiation emitted by cooler stars is mostly at wavelengths that are absorbed by ice, which heats it up. Tidal heating. If a planet has an eccentric orbit, then tidal heating can provide another source of energy besides stellar irradiation. This means that eccentric planets in the radiative habitable zone can be too hot for liquid water. Tides also circularize orbits over time, so there could be planets in the habitable zone with circular orbits that have no water because they used to have eccentric orbits. Eccentric planets further out than the radiative habitable zone would still have frozen surfaces, but the tidal heating could create a subsurface ocean similar to Europa's. In some planetary systems, such as in the Upsilon Andromedae system, the eccentricity of orbits is maintained or even periodically varied by perturbations from other planets in the system. Tidal heating can cause outgassing from the mantle, contributing to the formation and replenishment of an atmosphere. Potentially habitable planets. Confirmed planet discoveries in the habitable zone include the Kepler 22b, the first super-Earth located in the habitable zone of a Sun-like star. In September 2012, the discovery of two planets orbiting the red dwarf Gliese 163 was announced. One of the planets, Gliese 163c, about 6.9 times the mass of Earth and somewhat hotter, was considered to be within the habitable zone. In 2013, three more potentially habitable planets, Kepler 62e, Kepler 62f, and Kepler 69c, orbiting Kepler 62 and Kepler 69 respectively, were discovered. All three planets were super-Earths and may be covered by oceans thousands of kilometers deep. In June 2013, a dynamically packed planetary system around the nearby red dwarf Gliese 667c was announced. The system was found to contain at least 3 super-Earths in its habitable zone, establishing the new record in the number of potentially habitable worlds around a single star. The system contains 2 other planet candidates which would lie in the cold, hot edges of the star's habitable zone. This later result highlights the prevalence of low-mass stars as hosts of potentially habitable worlds. Earth-sized planets. In November 2013 it was announced that 22A plus or minus 8% of Sun-like stars have an Earth-sized planet in the habitable zone. Assuming 200 billion stars in the Milky Way, that would be 11 billion potentially habitable Earths, rising to 40 billion if red dwarf stars are included. Kepler 186f is the first Earth-sized planet in a habitable zone to have been discovered, a 1.1 Earth radius planet in the habitable zone of a red dwarf, announced in April 2014. In February 2013, researchers calculated that up to 6% of small red dwarfs may have planets with Earth-like properties. This suggests that the closest alien Earth to the Solar System could be 13 light-years away. The estimated distance increases to 21 light-years when a 95% confidence interval is used. In March 2013 a revised estimate based on a more accurate consideration of the size of the habitable zone around red dwarfs gave an occurrence rate of 50% for Earth-sized planets in the HZ of red dwarfs. Planetary systems. Orbital dynamics. Planetary systems can be categorized according to their orbital dynamics as resonant, non-resonant, interacting, hierarchical, or some combination of these. In resonant systems the orbital periods of the planets are in integer ratios. The Kepler 223 system contains 4 planets in an 8643 orbital resonance. In interacting systems, the planets' orbits are close enough together that they perturb the orbital parameters. The Solar System could be described as weakly interacting. In strongly interacting systems, Kepler's laws do not hold. In hierarchical systems, the planets are arranged so that the system can be gravitationally considered as a nested system of 2 bodies, for example in a star with a close-in hot Jupiter with another gas giant much further out. The star and hot Jupiter form a pair that appears as a single object to another planet that is far enough out. A system can contain bodies of different dynamical types, for example the Galilean moons of Jupiter were Io, Europa, and Ganymede are in resonance, but Callisto is too distant to be part of this resonance. Other, as yet unobserved, orbital possibilities include double planets, various co-orbital planets such as quasi-satellites, Trojans and exchange orbits, interlocking orbits maintained by precessing orbital planes, number of planets in a system and their relative masses, radii, orbital spacings and parameters, on the relative sizes of planets within Kepler multiple candidate systems, David Archiadi al. December 9, 2012, Architecture of planetary systems based on Kepler data, number of planets and planarity, Julia Fang, Jean-Luc Margot, October 30, 2012, Exoplanet predictions based on the generalized Titius-Bode relation, Timothy Boved, Charles H. Lineweaver, August 1, 2013, The Solar System and the Exoplanet Orbital Eccentricity, Multiplicity Relation, Mary Ann Limch, Edwin Alterna, April 9, 2014, Debris Disks, on the relationship between debris disks and planets, a GNES car-cubed SPA-L, David R. Ardila, Attila O cubed R, par copyright to Abraya M., June 30, 2009, signatures of exosolar planets in dust debris disks, Leonid M. Oznoy, Nick N. Gorkovai, John C. Mather, Tanya Tadakova, July 4, 2000, second and third generation planets, planets in evolved binary systems, Hogaibi Peretz, January 13, 2011, second generation planet formation in NN Serpentis. MVAR paragraph LSCHOW, Urbana G., F.V. Hessman, December 29, 2013, Engulfment by red giants, asymptotic giant branch stars and planetary nebulae, can planets survive stellar evolution? Eva Valeva, Mario Livio, February 2007, The Orbital Evolution of Gas Giant Planets Around Giant Stars, Eva Valeva, Mario Livio, October 13, 2009, on the survival of brown dwarfs and planets engulfed by their giant host star, Jean-Claude Passy, Mordecai Mark Maclow, Ursula De Marco, October 2, 2012, Foretellings of Ragnara paragraph K, World Engulfing Asymptotic Giants and the Inheritance of White Dwarfs, Alexander James Mustill, Eva Valeva, December 5, 2012, Cultural Impact, on May 9, 2013. A congressional hearing by 2 United States House of Representatives subcommittees discussed exoplanet discoveries. Have we found other Earths? Prompted by the discovery of exoplanet Kepler-62f, along with Kepler-62e and Kepler-62c. A related special issue of the journal Science, published earlier, described the discovery of the exoplanets. See also: exocomet, exomoon, extragalactic planet, list of exoplanet research projects, lists of extrasolar planets, notes. Further reading: Dormany, Bruce. Distant Wanderers. Springer Verlag. ISBN 978-0-387-95074-7 ISBN 978-1-4419-2872-6, Villard, Ray and Cook, Lynette. Our Infinite Worlds, An Illustrated Voyage to Planets Beyond Our Sun. University of California Press. ISBN 978-0-520-23710-0. Boss, Alan. The Crowded Universe, The Search for Living Planets. Basic Books. ISBN 978. -0-465-00936-7 ISBN 978-0-465-02039-3, Seeger, SARA Exoplanet Atmospheres, Physical Processes Princeton University Press ISBN 978-0-691-11914-4 ISBN 978-0-691-14645-4 Seeger, Sarah Exoplanets University of Arizona Press ISBN 978-0-8165-2945-2 Perryman, Michael The Exoplanet Handbook Cambridge University Press ISBN 978-0-521-76559-6 Jakob, Tyre Exoplanets and Alien Solar Systems New Earth Labs ISBN 978-0-974-16892-0 References. External links: The Extrasolar Planets Encyclopedia, NASA Exoplanet Archive, Open Exoplanet Catalog, the Habitable Exoplanets Catalog, the Habitable Zone Gallery, Exoplanet Orbit Data Explorer Interactive Table and Plotter for exploring data from Exoplanet Orbit Database, Exoplanets, Interactive Visual of XKCD 1071, Exoplanet Database for iPhone iPad with visualizations, NASA's Planet Quest, a zoo of extrasolar planets. AA Astronomy cast on February 9, 2009 with Pamela Gay and Chris Lintott, Transiting Exoplanet Light Curves Using Differential Photometry, Extrasolar Planets de Montes, UCM, Exoplanets at Paris Observatory, Exoplanets in relation to host stars current habitable. Zone planetarybiology.com. Doyle, Lawrence are naming new extrasolar planets. SETI Institute. Space.com. Retrieved June 2, 2010. Exoplanet Transit Database, ExoMol Project Spectroscopic Database of Molecules of Importance for the Characterization of Exoplanets. Characterizing Bulk Composition of Solid Planets, Graphical Comparison of Extrasolar Planets, Video Search for Life in the Universe NASA. News, Arxiv, Earth and Planetary Astrophysics, Extrasolar News and Discoveries, Astrobits The Astro PH Reader's Digest, Virtual Planetary Laboratory.